Everybody, in the lab this week, you're going to be using a Stella model, which is a very simple model to understand the relationships between different climate variables, things like CO2, albedo, and global temperature change. Now, when we want to predict the climate of the future, we need to use much more elaborate models. And the whole model technology has expanded greatly over the last 10 or 15 years. And basically what I wanted to do is tell you a little bit about what a model is and what these models can do and what they can't do. Okay, so basically a model is a physical representation of the Earth's climate. And what it does is it breaks the Earth's surface and its atmosphere into a network of grid cells. And these cells are roughly 200 kilometers in length and width. And I'm not quite sure how much the elevation is in this, the height in this model, but they're not that small. So maybe, 10 kilometers in height, something like that. And what a model does is it has physical relationships between the different grid cells. So for example, it exchanges energy between this grid cell here and that grid cell here, and exchanges energy between this grid cell here and that grid cell here. And the relationships between energy and climate drive the climate in the model. So what you do is you change a variable. So let's say, for example, we change albedo or we change CO2 level. You determine how that impacts the energy of an individual grid cell, and the energy of this individual grid cell, and then you physically represent how that drives the climate. And it's complex. Okay, so these models are massive. Stella you can run on your browser. A climate model you have to run on a very, very powerful mainframe type computer, and it takes a large amount of time. These are physically very complicated beasts. Okay, so what we have here is a representation of grids that drive the climate. And one of the main variables when we talk about the climate of the future is the concentration of CO2 in the atmosphere, because that's something that humans are impacting that will have a major effect on how much warming occurs. So what we have on the lower graph here are age over here, where we have the historic records here, and then here we are, well, this is today here, 2020, so this is an old plot. And then you have temperature change relative to the period between 1961 and 1990. And you can see moving forward, there's a huge difference in these model projections in terms of warming, varying from about 1.5 degrees centigrade, which in this RCP 2.6 is where you increase the amount of CO2 up to about 2040, and then it becomes flat. Okay, and that would be a good scenario. This is like the Paris Agreement we've been talking about. 1.5 degrees temperature rise. Climate change will be significant but not catastrophic. In the worst case scenarios where you increase CO2 levels, like the business as usual, where we just keep on dumping CO2 into the atmosphere, we keep on using fossil fuels, we don't go to renewable energy, things become a lot more dire. And you can see in this case, the 8.5 business as usual 2, which is the worst case scenario, that in the model projects that in 2100, temperature will increase by close to 4.5 degrees centigrade, which would be truly, 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 truly catastrophic for our planet. So the models help us get an understanding of what will happen in the future. But one of the main things that I want to show here is that different models, okay, and that's the variation here, the different models show very different results. So there are about 29, 30 commonly used climate models, and each one will give different physical representations here. So the detailed way that energy flows between grids is different in these different models, and that therefore they give different results. That's why you see quite a number of blue, quite a bit of variation in the blue, quite a bit of variation in the orange and the green, and then in the red. So different models will show different amount of warming based on these CO2 levels. All right, so that's kind of a rough introduction to models. They're very, very useful. The IPCC that we'll be talking about often in this course use different models and show the variation with different models, and they basically allow us to project into the future. And no doubt about it, it's very clear that the vital constraint here is the amount of CO2 we put into the atmosphere. If we level it off quickly, temperature doesn't rise. If we just keep on putting it in the way we're putting it in now, things get out of hand quickly.